Picture holding a marble in your palm. Feel its smooth surface, its perfect roundness, its weight. Now imagine that this tiny sphere contains everything that would ever exist. Every star, every galaxy, every atom that would one day form planets, oceans, and even you. This marble represents our universe at its very beginning, compressed into a space smaller than the period at the end of this sentence. How big was the universe right after the Big Bang? This question takes us to the very edge of human understanding, to a moment so extraordinary that it challenges everything we think we know about space, size, and existence itself. We're about to embark on a journey that will stretch your imagination from the infinitesimally small to the incomprehensibly vast, from the first fraction of a second to the cosmic architecture we see today. You might think this is a simple question, with a straightforward answer: just measure the universe and work backward. But as we'll discover, the reality is far more mind-bending than you could imagine. The universe wasn't just small after the Big Bang, it existed in a state so alien to our everyday experience that our normal concepts of size and distance break down entirely. What we're about to explore will take us through the most violent and creative moments in cosmic history, when the laws of physics themselves were being written. We'll witness the birth of space and time, the emergence of matter from pure energy, and the incredible expansion that transformed a point smaller than an atom into the observable universe we see today. So take a moment to really feel that marble in your hand, because by the end of our journey, you'll understand how something smaller than that marble became the stage for everything we've ever known, and you'll never look at the night sky the same way again. Let's dive into the cosmic mystery of the universe's first moments, and discover just how big, or impossibly small, everything once was. To understand how big the universe was right after the Big Bang, we first need to grasp what we mean by right after. When cosmologists talk about the beginning of the universe, they're not referring to some arbitrary starting point in an empty void. They're describing the emergence of space and time themselves, a moment so fundamental that asking what came before it is like asking what's north of the North Pole. Let's start our journey with a brilliant mind from the early 20th century. In 1927, a Belgian priest and physicist named Georges Lemaitre proposed something that seemed absurd to his contemporaries. The universe was expanding. Not only that, but if you could run time backward like a cosmic movie in reverse, you'd see everything contracting until it reached what he called the primeval atom, a single point containing all of existence. Picture this primeval atom as the ultimate seed. But unlike any seed you've ever seen, this one contained not just the potential for life, but the potential for space itself. When Lemaitre first proposed this idea, even Einstein rejected it, famously saying that while the mathematics might work, the physics was abominable. The very notion that the universe could have a beginning contradicted the prevailing view of an eternal, unchanging cosmos. Yet the evidence kept mounting. In the 1920s, Edwin Hubble made observations that would revolutionize our understanding of the universe. Using the then-new 100-inch telescope at Mount Wilson Observatory, Hubble discovered that distant galaxies were moving away from us, and the farther they were, the faster they receded. This relationship, now known as Hubble's law, provided the first concrete evidence for an expanding universe. But here's where things get truly mind-bending. When we say the universe was smaller in the past, we're not talking about stuff being squeezed into a smaller container. We're talking about space itself being smaller. Imagine you're an ant walking on the surface of a balloon. As someone inflates the balloon, you notice that every landmark you can see is moving away from you. The balloon surface, your entire two-dimensional universe, is expanding, carrying everything with it. Now let's zoom in on those crucial first moments. Scientists have identified specific epochs in the universe's early history, each characterized by different physical conditions and sizes. The very first moment we can meaningfully discuss is called the Planck epoch, occurring from time 0 to about 1043, 43 seconds after the Big Bang. This unimaginably brief instant, a decimal point followed by 42 zeros and then a 1, represents the smallest unit of time that has any physical meaning. During the Planck epoch, the observable universe, the part we can potentially see today, was compressed into a region smaller than 10 or 35 meters across. To put this in perspective, this distance is to an atom what an atom is to a sphere 10 kilometers wide. It's so small that our normal concepts of measurement become meaningless. At this scale, space and time themselves become fuzzy and uncertain, dancing to the strange rhythm of quantum mechanics. Think about holding that marble again. Now imagine shrinking it down until it's the size of a pinhead. Keep shrinking it until it's the size of a dust mote, then a molecule, then an atom, then an atomic nucleus. Keep going. You're still nowhere near the size of the observable universe during the Planck epoch. You'd need to shrink that nucleus by a factor of about 100 million billion to reach the Planck length. But here's what makes this even more extraordinary. This infinitesimally small region contained all the energy that would eventually become the 100 billion galaxies we observe today. The density was so extreme that a teaspoon of this primordial matter would weigh more than all the mountains on Earth combined. In fact, more than the entire Earth itself. As we move forward in time, the universe undergoes a period called cosmic inflation. This isn't the steady expansion we observe today, but an exponential stretching of space itself that occurred between about 1036 and 10 32 seconds after the Big Bang. During this brief period, shorter than the time it takes light to travel, across a proton, the observable universe expanded by a factor of at least 10 to 26. If a grain of sand inflated by the same factor, it would become larger than our solar system. The theory of cosmic inflation was proposed by physicist Alan Guth in 1980 to solve several puzzles about the universe's structure. Before Guth's work, cosmologists struggled to explain why the universe appears so uniform in temperature and density across vast distances that should never have been in contact with each other. Inflation provides an elegant solution. Regions that are now billions of light-years apart were once close enough to exchange energy and reach thermal equilibrium. During inflation, the size of the observable universe grew from roughly 10⁻35 meters to about 10⁻49 meters, roughly the size of a grapefruit. This might not sound like much, but remember that this expansion factor of 10⁻26 represents one of the most dramatic changes in the history of the cosmos. It's as if every point in space suddenly found itself in a universe 100 million billion times larger than before. But what drove this incredible expansion? The answer lies in a hypothetical field called the inflaton field. Like a ball rolling down a hill, this field carried enormous potential energy. As it slowly rolled toward a lower energy state, it drove the exponential expansion of space. When the field finally reached the bottom of its energy hill, inflation ended in a process called reheating, where the field's energy was converted into the hot, dense plasma of ordinary matter and radiation. After inflation ended at around 10⁻32 seconds, the universe entered what cosmologists call the radiation-dominated era. The observable universe was now roughly the size of a beach ball, still incredibly hot ball, still incredibly hot and dense, but beginning to follow the more familiar pattern of gradual expansion we see today. The temperature was still an unimaginable 10 to 28 degrees Kelvin, 80 billion times hotter than the center of the sun. As the universe continued to expand and cool, fundamental forces began to separate from their unified high-energy state. First, gravity split off during the Planck epoch. Then, during what's called the Grand Unification epoch, the strong nuclear force separated from the electroweak force. Finally, at around 10 TD, 2012 seconds after the Big Bang, the electromagnetic and weak nuclear forces separated, giving us the four fundamental forces we know today. By the time the universe was 1 second old, it had grown to roughly the size of our solar system. The temperature had dropped to about 10 billion degrees Kelvin, still incredibly hot, but cool enough for protons and neutrons to form from the quark-gluon plasma that had dominated earlier epochs. This moment marks the beginning of Big Bang, nucleosynthesis, when the first atomic nuclei began to form. Here's something remarkable to consider. During these first moments, the universe was simultaneously the smallest and most energetic it has ever been. Every cubic centimeter contained more energy than we could produce with all of our power plants combined. Yet this same universe would eventually become the cold, sparse cosmos we inhabit today, where galaxies are separated by millions of light years of nearly empty space. The transition from that initial cosmic seed to our current universe represents one of the most extraordinary transformations in physics. It's a story of how quantum fluctuations, tiny random variations in energy at the smallest scales, were stretched by inflation to become the seeds of all cosmic structure. The galaxies, stars, and planets we see today all trace their origins back to infinitesimal variations in that primordial marble-sized universe. As we stand here today, looking up at the night sky, we're seeing the result of that ancient expansion. The most distant galaxies we can observe with our most powerful telescopes appear as they were when the universe was just a few 100 million years old, cosmic toddlers compared to the 13.8 billion-year-old universe we inhabit now. Yet even these young galaxies were already separated by millions of light years, a testament to the incredible expansion that began in those first fractions of a second. Understanding the size of the early universe isn't just an academic exercise, it's key to understanding why the cosmos looks the way it does today. The horizon problem, the flatness problem, and the monopole problem that plagued earlier cosmological models all find their solutions in the physics of that marble-sized beginning. It's a reminder that sometimes the most profound truths about our universe are hidden in its most extreme and alien moments. Now that we've established the incredible smallness of the early universe, let's dive deeper into the mathematical framework that describes how we actually calculate these mind-boggling numbers. The story of cosmic expansion isn't just a tale of things getting bigger. It's a precise mathematical dance governed by Einstein's equations, quantum mechanics, and the mysterious properties of space-time itself. To truly understand how big the universe was after the Big Bang, we need to master a crucial concept, the scale factor. Imagine the universe as a rubber sheet with galaxies painted on it. As the sheet stretches, the galaxies move apart, but they're not actually moving through space. Space itself is expanding, carrying them along. The scale factor, usually denoted as AT, tells us how much larger the universe is at any given time, compared to some reference point. Albert Einstein never intended his theory of general relativity to describe an expanding universe. In fact, when he first developed his field equations in 1915, he was so convinced the universe was static that he added a cosmological constant, a kind of anti-gravity term, to keep everything from collapsing under its own gravitational pull. When Hubble's observations later confirmed expansion, Einstein called this cosmological constant his greatest blunder. But Einstein's equations, even without his cosmological constant, naturally described an evolving universe. In the 1920s, Russian physicist Alexander Friedmann solved Einstein's field equations for a homogeneous, isotropic universe, one that looks the same in all directions and at all locations when viewed on the largest scales. His solutions, now called the Friedmann equations, form the mathematical backbone of modern cosmology. The key Friedmann equation tells us how the scale factor changes with time. It looks deceptively simple, but contained within its elegant mathematical structure is the entire history of cosmic expansion. The equation shows that the expansion rate depends on the density of matter, radiation, and dark energy in the universe, as well as the curvature of space-time itself. Let's think about this with a thought experiment. Imagine you're a cosmic archaeologist, trying to piece together the universe's history by observing distant galaxies. When you look at a galaxy 1 billion light-years away, you're seeing it as it was 1 billion years ago. The light has been traveling toward you all that time. But here's the crucial insight. During its journey, space itself has been expanding. This means the galaxy was actually much closer when it emitted the light you're now seeing. If the universe has doubled in size since then, that galaxy was only 500 million light-years away when it emitted the photons reaching your telescope today. This is why cosmologists can work backward from current observations to determine the size of the universe at any point in its history. The mathematics becomes even more fascinating when we consider the early universe. During the radiation-dominated era, which lasted from the end of inflation until about 50,000 years after the Big Bang, the scale factor grew proportionally to the square root of time. This means that if you wanted to know how much bigger the universe was after 2 seconds compared to 1 second, you'd calculate the square root of 2, which is about 1.41. So the universe was about 41% larger after 2 seconds than after 1 second. But during the inflation period, the mathematics tells a completely different story. The scale factor grew exponentially, meaning it doubled over and over again at regular intervals. If the doubling time was about 10 to 37 seconds, then in just 60 doubling periods, a span of time so brief that light couldn't travel the width of a proton, the universe expanded by a factor of 260, which is more than 1 billion. Here's where the math becomes truly mind-bending. We can use the Friedmann equations to trace the observable universe back to its starting size. Today, the observable universe has a radius of about 46.5 billion light-years. But remember, this isn't how far light has traveled. It's how far away. The most distant observable objects are now accounting for the expansion of space during the light's journey. Working backward through the mathematics, we find that at the end of inflation, about 10 to 32 seconds after the Big Bang, the currently observable universe was about the size of a grapefruit. Before inflation began, at around 10 to 36 seconds, it was smaller than a proton. And at the Planck time, 10 to 43 seconds after the Big Bang, it was incomprehensibly smaller, about 10 to 35 meters across. To truly appreciate these numbers, let's put them in perspective using powers of 10. The Planck length, 10 to 35 meters, is, to an atom, about 10 meters, as an atom is to something 10 to weight, 15 meters across. That's about the distance from Earth to the Sun and back again, 6 times over. We're dealing with scales so extreme that they challenge our ability to visualize or even comprehend them. The mathematics also reveals something profound about the nature of space and time. During the Planck epoch, the Heisenberg uncertainty Principle tells us that our classical notions of space and time break down entirely. At scales smaller than the Planck length and time intervals shorter than the Planck time, quantum fluctuations become so violent that space-time itself becomes a frothy, ever-changing quantum foam. This is where our mathematical models reach their limits. We can calculate backward to the Planck epoch, but beyond that, we need a theory of quantum gravity, something that combines Einstein's relativity with quantum mechanics. String theory, loop quantum gravity, and other approaches attempt to bridge this gap, but we don't yet have definitive answers about what happens at the very beginning. One of the most remarkable aspects of the early universe's mathematics is how tiny quantum fluctuations were amplified to cosmic scales. During inflation, quantum uncertainty at the subatomic level was stretched across space faster than light could travel. These stretched quantum fluctuations became the seeds of all large-scale structure in the universe, the slight density variations that would eventually grow into galaxies, galaxy clusters, and the cosmic web we observe today. The mathematics of inflation is based on quantum field theory, which describes particles as excitations in underlying fields that permeate all of space. The inflaton field that drove cosmic expansion was subject to quantum fluctuations, random variations in its energy density at every point in space. As space expanded exponentially, these microscopic fluctuations were stretched to macroscopic scales, creating a pattern of slight overdensities and underdensities that we can still observe today in the cosmic microwave background radiation. Let's see. Consider the energies involved during these early moments. The energy density during the Planck epoch was approximately 5 VeV x 10^-113 joules per cubic meter. To put this in perspective, this is more energy in a volume the size of a proton than our Sun produces in its entire 10 billion-year lifetime. The mathematics tells us that at these energy densities, the distinction between matter and energy becomes meaningless. Everything exists as pure energy in its most fundamental form. As the universe expanded and cooled, phase transitions occurred. At specific temperatures and times, much like water turning to ice as it cools. The mathematics of these phase transitions helps us understand how the four fundamental forces separated from their unified high-energy state. Each transition left its mark on the structure and properties of the universe, creating the physical laws and constants we observe today. The Friedmann equations also predict something counterintuitive about the early universe. Despite being incredibly dense and hot, it was actually expanding faster than it is today. The expansion rate, described by the Hubble parameter, was inversely proportional to the age of the universe during the radiation-dominated era. When the universe was 1 second old, it was expanding about 400 billion times faster than it is now. This rapid early expansion had profound consequences for the size calculations we're exploring. It means that during the first few minutes after the Big Bang, the observable universe grew from roughly the size of our solar system to about 100 light-years across. In just those few minutes, less time than it takes to watch a movie, space expanded by a factor of about 10 million. The mathematics also reveals the crucial role of dark energy in the universe's expansion history. While dark energy has only dominated cosmic expansion for the last few billion years, its effects can be traced backward through the equations. During the early universe, however, matter and radiation were so dense that dark energy's influence was negligible. It's only as the universe expanded and diluted that dark energy became the dominant component driving cosmic acceleration. 1. Of the most elegant aspects of cosmic expansion, mathematics is how it connects the smallest and largest scales in the universe. The same equations that describe how the universe grew from smaller than an atom to its current size also predict the formation of the cosmic web, the largest structures in the universe, with galaxy filaments stretching across hundreds of millions of light-years. But perhaps the most profound mathematical insight is this: the very question, how big was the universe right after the Big Bang, might be based on a false assumption. The mathematics suggests that the universe might be infinite in extent, meaning it was infinite even at the moment of the Big Bang. What we call the size of the early universe is really the size of the observable portion, the region from which light has had time to reach us. If the universe is indeed infinite, then the Big Bang wasn't an explosion from a point into empty space, but rather a moment when every point in an infinite space began, expanding simultaneously. This is a mathematically consistent picture that emerges from the Friedmann equations, though it challenges our everyday intuitions about beginnings and boundaries. The mathematics of cosmic expansion has led to one of the most startling conclusions. In modern physics, the universe we can observe today all originated from a region smaller than the period at the end of this sentence. Every atom in your body, every star in the sky, every galaxy we can see through our most powerful telescopes, all of it was once compressed into a space so small that it defies comprehension. Yet this same mathematics gives us hope for understanding even deeper truths about reality. As we develop better theories that unify quantum mechanics and gravity, we may finally be able to peer beyond the Planck epoch and understand what, if anything, came before the Big Bang. The mathematics that revealed the universe's tiny beginning may ultimately show us that beginning itself was just another transformation in an even grander cosmic story. Now we enter perhaps the most extraordinary chapter in the universe's history, a period so bizarre and violent that it transformed our understanding of reality itself. Between 10^36 and 10^32 seconds after the Big Bang, the universe underwent an exponential expansion so rapid and dramatic that it makes today's cosmic expansion look positively sluggish. This is cosmic inflation, and understanding it is crucial to answering how big the universe was in its earliest moments. Imagine holding a grain of sand and watching it suddenly expand to the size of a basketball in less than a billionth of a trillionth of a trillionth of a second. That's still not fast enough to match what happened to the universe during inflation. In this brief moment, the observable universe expanded by a factor of at least 10 to the 26. That's a 1 followed by 26 zeros. To put this in perspective, if an atom inflated by the same amount, it would become larger than a grapefruit. The story of inflation begins with a profound puzzle that cosmologists faced in the 1970s. The universe appeared remarkably uniform in temperature when viewed on the largest scales. Regions of space that were billions of light-years apart had almost exactly the same temperature, as measured in the cosmic microwave background radiation. But according to the standard Big Bang model, these regions should never have been in contact with each other. Light hadn't had enough time since the Big Bang to travel between them and establish thermal equilibrium. This became known as the horizon problem, and it seemed to violate one of the fundamental principles of physics. Nothing can travel faster than light. How could distant regions of the universe know to have the same temperature if they had never been in causal contact? It was like finding that every person on Earth was wearing the exact same outfit without any communication between them. Enter Alan Guth, a young particle physicist working at Stanford in 1979. Guth was studying the behavior of exotic particles in the early universe when he stumbled upon a remarkable possibility. Under certain conditions, the universe could have undergone a period of exponential expansion driven by a peculiar form of energy that created a kind of cosmic anti-gravity. He called this process inflation, and it would revolutionize our understanding of the universe's birth. The key to inflation lies in understanding a quantum field called the inflaton. Think of this field as an invisible ocean that filled all of space in the early universe. Unlike ordinary matter or radiation, this field had a very unusual property. Instead of causing space to contract under its gravitational pull, it caused space to expand exponentially. The field acted like a cosmic repulsive force, pushing space apart faster and faster with each passing moment. But here's what makes inflation truly mind-bending. During this period, space itself was expanding faster than the speed of light. You might think this violates Einstein's prohibition against faster-than-light travel, but it doesn't. Einstein's speed limit applies to objects moving through space, not to space itself. There's no cosmic speed limit for the expansion of space-time. It can stretch at any rate whatsoever. During inflation, the scale factor of the universe doubled approximately every 10^37 seconds. In the time it takes light to travel across a proton, the universe doubled in size. Then it doubled again. And again. By the time inflation ended, after roughly 60 doublings, the universe had expanded by a factor of 2 times 60, which equals about 10^18. This is a conservative estimate. Some models suggest the expansion factor could have been as large as 10 to 30 or even greater. To truly grasp the implications of this expansion, let's follow the journey of 2 points that were initially separated by the Planck length, the smallest meaningful distance in physics. Before inflation, these points were about 10 to 35 meters apart, closer together than we can even meaningfully describe. After inflation, they would be separated by about 1 meter, roughly the distance from your fingertips to your shoulder when you stretch out your arm. This exponential stretching solved the horizon problem elegantly. Regions that appear disconnected today were actually in close contact before inflation began. They had time to reach thermal equilibrium during the Planck epoch, and then inflation stretched them to cosmic scales while preserving their uniform temperature. It's like taking a photograph and blowing it up a trillion times. Every pixel retains its original properties, but is now spread across a vast area. But inflation solved more than just the horizon problem. It also explained why space appears to be geometrically flat on the largest scales. Before inflation, the observable universe might have had a significant curvature, positive or negative. But just as inflating a balloon makes its surface appear flatter and flatter to a small observer on its surface, cosmic inflation stretched any initial curvature until space appeared essentially flat within our observable horizon. The inflaton field that drove this expansion was unlike anything we encounter in everyday life. It was a scalar field, meaning it had the same value in all directions at any given point, and it was slowly rolling down what physicists call a potential energy hill. As long as the field remained near the top of this hill, it maintained a nearly constant energy density even as space expanded, driving the exponential growth. Think of the inflaton field like a ball rolling down a very flat hill. Gravity pulls the ball downward, but the slope is so gentle that it rolls extremely slowly. In the meantime, the ball's position near the top of the hill maintains a high potential energy that drives cosmic expansion. When the ball finally reaches the bottom of the hill, inflation ends in a dramatic process called reheating. During reheating, the inflaton field's potential energy was converted into ordinary matter and radiation, heating the universe to tremendous temperatures and beginning the more familiar radiation-dominated era of cosmic evolution. This transition happened around 10 to 32 seconds after the Big Bang, when the observable universe had grown from its pre-inflation size of about 10 times 35 meters to roughly 10 times 9 meters, about the size of a grapefruit. The beauty of inflation lies not just in solving existing problems, but in making testable predictions. If inflation really occurred, it should have left specific signatures in the cosmic microwave background radiation, the afterglow of the Big Bang that we can observe today. These signatures include tiny temperature fluctuations that follow a specific pattern predicted by inflation theory. The predictions have been spectacularly confirmed by observations. The Cosmic Background Explorer, COBE, satellite first detected the predicted fluctuations in the 1990s. The Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have since measured these fluctuations with exquisite precision, finding them to match inflation's predictions to remarkable accuracy. But inflation also predicted something even more extraordinary: gravitational waves from the inflationary epoch itself. As space expanded exponentially, it should have produced ripples in the fabric of space-time that we might detect today as primordial gravitational waves. Several experiments, including the BICEP telescopes at the South Pole and the upcoming Laser Interferometer Space Antenna, LISA, are searching for these cosmic fossils from inflation. The quantum nature of inflation adds another layer of wonder to this story. During the inflationary epoch, quantum fluctuations in the inflaton field were stretched to macroscopic scales, creating tiny variations in the energy density throughout space. These quantum fluctuations, magnified by inflation, became the seeds of all structure in the universe, the slight overdensities that would eventually collapse under gravity to form stars, galaxies, and galaxy clusters. This means that the cosmic web we observe today, the intricate pattern of galaxy filaments, separated by vast cosmic voids, all traces back to quantum uncertainty during inflation. The uncertainty principle that governs atomic physics also shaped the largest structures in the universe. It's a profound connection between the quantum and cosmic realms that inflation makes possible. Recent observations have added new chapters to the inflation story. The James Webb Space Telescope has observed galaxies that existed when the universe was less than 400 million years old, cosmic time when the effects of inflation were still shaping galaxy formation. These observations provide new tests of inflation, models, and help us understand how the tiny seeds planted during inflation grew into the cosmic structures we see today. Different models of inflation make different predictions about the details of this process. Single-field inflation models, where one inflaton field drives the entire process, make specific predictions about the pattern of fluctuations we should observe. Multi-field models, where several fields interact during inflation, can produce more complex patterns. Eternal inflation models suggest that inflation continues forever in some regions of space, constantly creating new pocket universes like our own. The energy scale of inflation was truly staggering. Theoretical calculations suggest that the energy density during inflation was about 10^73 joules per cubic meter, roughly equivalent to the mass energy of a billion protons packed into a space the size of a proton. This is energy density beyond anything we can create in our most powerful particle accelerators, approaching the fundamental energy scale where gravity becomes as strong as the other forces of nature. Understanding inflation has also revealed something profound about the nature of empty space itself. What we call the vacuum, supposedly empty space, is actually filled with quantum fields that fluctuate according to the uncertainty principle. During inflation, these vacuum fluctuations were amplified and stretched to cosmic scales, becoming the foundation for all the structure we see in the universe today. This leads to a startling conclusion. Everything we observe in the universe, every star, planet, and living being, owes its existence to quantum fluctuations in empty space that were amplified by inflation. In a very real sense, we are all children of the quantum vacuum, products of uncertainty made manifest on cosmic scales. The end of inflation marks one of the most important phase transitions in cosmic history. As the inflaton field reached the bottom of its potential energy hill, it decayed into ordinary particles, filling the universe with a hot, dense plasma of quarks, leptons, and photons. The exponential expansion ended, replaced by the more sedate power law expansion that continues today. But here's the truly mind-bending part. If inflation happened once, it could happen again. Some models suggest that inflation is eternal, constantly, creating new regions of space that undergo their own inflationary epochs. Our observable universe might be just one bubble in an infinite cosmic foam, each bubble the product of its own inflationary expansion. This possibility raises profound questions about the nature of existence itself. If eternal inflation is correct, then there might be an infinite number of universes, each with its own laws of physics and cosmic history. Our universe, with its specific properties that allow for stars, planets, and life, might be just one possibility among an infinite multiverse of realities. As we stand here today, 13.8 billion years after the Big Bang, we're living in the aftermath of that brief but extraordinary inflationary epoch. The fact that you can read these words, that Earth orbits a stable star, that galaxies cluster together in the cosmic web, all of it traces back to those first fractions of a second, when the universe expanded faster than light itself, transforming quantum whispers into the cosmic symphony we observe today. The next time you look up at the night sky, remember that every photon reaching your eyes has traveled across a universe shaped by inflation. The space between the stars, the very fabric of reality itself, bears the imprint of that ancient exponential expansion. In understanding inflation, we've not just solved puzzles about the early universe. We've discovered that the cosmos itself is far stranger and more wonderful than we ever imagined. As our cosmic journey continues, we now venture into the realm where the infinitesimally small meets the infinitely large, where quantum mechanics shapes the destiny of galaxies, and where the uncertainty principle becomes the architect of cosmic structure. To truly understand how big the universe was after the Big Bang, we must explore how quantum fluctuations during those first moments became the seeds of everything we see today. Picture this. During the earliest moments after the Big Bang, space itself was not the smooth, continuous fabric we imagine today. At the Planck scale, space-time writhed and fluctuated like a storm-tossed ocean, with virtual particles popping in and out of existence in accordance with Heisenberg's uncertainty principle. This is what physicists call quantum foam, a frothy, ever-changing tapestry of space and time at the smallest scales. In our everyday experience, uncertainty is something we can minimize with better measurements and more precise instruments. But quantum uncertainty is fundamentally different. It's not a limitation of our measurement tools. It's a basic feature of reality itself. At scales smaller than the Planck length, 10 to 35 meters, the very concepts of distance and time become probabilistic rather than definite. During the universe's first 10 to 43 seconds, the Planck epoch, the observable universe existed in this quantum foam state. Every point in space was subject to violent quantum fluctuations, with energy densities fluctuating wildly on timescales shorter than the Planck time. These weren't gentle ripples on a cosmic pond. They were titanic variations in the fabric of reality itself, where the distinction between matter, energy, space, and time became meaningless. Werner Heisenberg, who formulated the uncertainty principle in 1927, could never have imagined that his quantum mechanical insights would one day explain the origin of galaxies. Yet, that's exactly what happened. The uncertainty principle tells us that the more precisely we try to define the energy of a quantum field at a particular moment, the more uncertain we become about how that energy changes over time. This creates unavoidable fluctuations in the energy density of any quantum field, including the inflation field that drove cosmic expansion. During inflation, these quantum energy fluctuations had a remarkable property. They were frozen into the expanding fabric of space-time. As space expanded exponentially, wavelengths that were initially smaller than a proton were stretched to sizes larger than our current solar system. Quantum fluctuations that began as microscopic whispers in the quantum foam became macroscopic variations in the energy density of the universe. Think of it like a symphony being recorded on a rubber sheet. As you stretch the sheet, the wavelengths of the music get longer and longer, but the relative pattern of notes remains the same. During inflation, quantum fluctuations were similarly stretched, preserving their pattern while amplifying their scale by factors of 10 to 26 or more. This process created what cosmologists call a nearly scale-invariant spectrum of fluctuations. This means that the strength of the fluctuations was roughly the same at all scales, a signature that we can still observe today in the cosmic microwave background radiation. When we look at the temperature variations in this ancient light, we're seeing the direct imprint of quantum fluctuations from the first moments of cosmic history. But the story doesn't end with inflation. After the inflationary epoch ended, these frozen fluctuations became the seeds for all subsequent cosmic evolution. Regions with slightly higher energy density had a stronger gravitational pull, attracting surrounding matter. Regions with lower density became cosmic voids. Over millions and billions of years, these tiny quantum seeds grew into the cosmic web, the largest structures in the observable universe. Recent observations from the James Webb Space Telescope have provided unprecedented glimpses into this cosmic construction process. JWST has detected galaxies that formed when the universe was less than 400 million years old, showing us how the first stars and galaxies assembled around the gravitational scaffolding created by inflation. These early galaxies appear surprisingly massive and mature for their young age, suggesting that the quantum seeds from inflation were remarkably efficient at concentrating matter and triggering star formation. The mathematics of this process is breathtakingly elegant. Einstein's theory of general relativity describes how matter and energy curve space-time, while quantum field theory describes the fluctuations that create variations in that matter and energy. When combined, these theories predict exactly the pattern of cosmic structure we observe today. Galaxy clusters connected by filaments of dark matter and ordinary matter, separated by vast cosmic voids where few galaxies exist. Consider the scale of this transformation. A quantum fluctuation that began with an amplitude of perhaps 10^5, a variation of just 1 part in $100,000, has grown over 13.8 billion years into structures spanning hundreds of millions of light years. The Coma cluster, one of the largest galaxy clusters we can observe, contains thousands of galaxies and has a total mass more than 10^15 times that of our Sun. All of this cosmic architecture traces back to a quantum fluctuation smaller than the nucleus of an atom. But quantum mechanics didn't just create the largest structures in the universe. It also determined their statistical properties. The uncertainty principle creates what mathematicians call a Gaussian distribution of fluctuations, meaning that small variations are common while large variations are rare. This prediction matches observations with remarkable precision. Most regions of space have density variations close to the average, while extremely dense regions, like the cores of galaxy clusters, and extremely empty regions, like cosmic voids, are much rarer. The quantum origin of cosmic structure also explains one of the most puzzling features of our universe, its isotropy. When we look in any direction, we see roughly the same density of galaxies, the same temperature in the cosmic microwave background, and the same overall structure. This isotropy exists because the quantum fluctuations that seeded cosmic structure were essentially random. There was no preferred direction in the quantum foam of the early universe. Yet within this overall isotropy, we find a rich tapestry of structure. The cosmic web exhibits a fractal-like quality, with structure on structure. At every scale we can observe. Galaxy clusters are connected by filaments. Galaxies within clusters show substructure. And even individual galaxies contain spiral arms, bars, and satellite dwarf galaxies. All of this hierarchical complexity emerged from the simple, random, quantum fluctuations of the inflationary epoch. Modern cosmological simulations allow us to follow this process in detail. Supercomputers running the Millennium simulation and its successors have modeled the growth of cosmic structure from the initial quantum fluctuations to the present day. These simulations show how tiny density variations grow under gravity, merge, and collide, and eventually form the cosmic web we observe. The agreement between these simulations and actual observations provides powerful confirmation that we understand the quantum origin of cosmic structure. But the quantum story of the early universe reveals something even more profound about the nature of reality itself. During the Planck epoch, when the observable universe was smaller than 10 to the 35 meters, the boundary between the quantum and classical worlds completely disappeared. There was no clear distinction between wave and particle, between matter and energy, or even between space and time. The universe existed in a pure quantum state, a superposition of all possible configurations of space-time. This quantum superposition ended with the process cosmologists call decoherence. As the universe expanded and cooled, interactions between different parts of the quantum system caused the universal wave function to collapse into a specific classical configuration. The universe chose one particular arrangement of matter and energy from among the infinite quantum possibilities, and that choice determined everything about the cosmos we inhabit today. Some interpretations of quantum mechanics suggest that this decoherence process didn't eliminate the other possibilities, but instead created parallel universes for each quantum alternative. According to the many worlds interpretation, there might be countless other universes where the quantum fluctuations during inflation played out differently, creating entirely different patterns of cosmic structure. Our universe, with its specific arrangement of galaxies and voids, represents just one branch of a vast quantum multiverse. The transition from quantum to classical behavior also marked the emergence of what we call cosmic time, a universal clock that ticks the same for all observers in the expanding universe. Before this transition, during the Planck epoch, even the concept of simultaneity was meaningless. There was no universal now that applied throughout space. The emergence of classical space-time created the temporal framework within which cosmic evolution could proceed. Understanding this quantum to classical transition helps us appreciate why the question, "How big was the universe right after the Big Bang?" is so profound. We're not just asking about the size of a container filled with matter. We're asking about the emergence of space and time themselves from a purely quantum state. The size of the early universe is really a measure of how much space-time had crystallized out of the quantum foam. Recent developments in quantum gravity theories are providing new insights into this process. Loop quantum cosmology suggests that the Big Bang wasn't actually a beginning, but rather a quantum bounce, a transition from a previous contracting universe to our expanding one. In this picture, the size of the universe at the bounce was determined by quantum geometry effects that prevent matter from collapsing to a true singularity. String theory offers another perspective, proposing that the fundamental constituents of reality are not point particles, but tiny vibrating strings, existing in higher dimensional space. In some string cosmology models, our three-dimensional universe emerged from the collision of higher dimensional membranes, with the quantum fluctuations in these membranes determining the initial conditions for cosmic evolution. These gravity theories suggest that the universe's minimum size might not be zero, but rather some finite quantum length scale, possibly the Planck length itself. If true, this would mean that the universe was never smaller than about 10⁻35 meters, even at the moment of the Big Bang. The apparent singularity predicted by classical general relativity would be resolved by quantum effects, leaving us with a universe that has a definite minimum size determined by the fundamental constants of nature. The quantum nature of the early universe also has implications for one of the deepest questions in cosmology. Why does the universe contain more matter than antimatter? According to our current understanding of particle physics, the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a universe filled only with radiation. The fact that we exist proves this didn't happen. The solution might lie in quantum processes during the early universe that violated the symmetry between matter and antimatter. These processes, called baryogenesis mechanisms, could have operated during phase transitions in the first fraction of a second after the Big Bang, when the universe was still smaller than an atomic nucleus. The quantum nature of these processes means that tiny violations of matter-antimatter symmetry could be amplified to create the matter-dominated universe we observe today. As we trace the universe's evolution from quantum foam to cosmic architecture, we see a remarkable pattern. Quantum effects that were most important when the universe was smallest continue to influence its largest-scale properties today. The quantum fluctuations frozen into space-time during inflation determine where galaxies form. The quantum nature of dark matter particles affects how cosmic structure evolves. Even the accelerating expansion of the universe might be driven by quantum vacuum energy, the same quantum fluctuations that filled the universe during its first moments. This deep connection between the quantum and cosmic realms suggests that understanding the size of the early universe requires us to fundamentally reimagine our concepts of space, time, and existence itself. The universe wasn't simply a small object that grew larger. It was a quantum possibility that became a classical reality, transforming from a superposition of all possible spacetimes into the specific cosmos we inhabit. The implications extend beyond cosmology into philosophy and our understanding of consciousness itself. If the universe began as a quantum superposition and chose its current configuration through decoherence, what role, if any, did observation play in this process? Some interpretations suggest that consciousness itself might be a fundamental feature of the universe, helping to collapse quantum possibilities into classical reality. As we continue our journey through cosmic history, remember that every atom in your body was forged in the heart of a star that formed around a gravitational seed created by quantum fluctuations during inflation. You are literally made of processed starlight, and that starlight exists because of quantum uncertainty in the first moments after the Big Bang. The connection between your existence and the quantum nature of the early universe is not metaphorical. It's a direct causal chain stretching back 13.8 billion years to when the observable universe was smaller than the nucleus of an atom. In the next phase of our journey, we'll explore how these quantum seeds grew into the cosmic structures we observe today, and how the continued expansion of space itself shapes the universe's ultimate destiny. But first, take a moment to marvel at the profound truth we've uncovered. The largest structures in the universe owe their existence to the smallest scales of reality. where quantum mechanics reigns supreme, and the very notion of definite size becomes beautifully, mysteriously uncertain. As we continue our cosmic odyssey, we now witness one of the most remarkable transformations in the universe's history: the transition from a featureless quantum realm to the rich, structured cosmos we see today. After inflation ended and the universe entered its more familiar expansion phase, the tiny quantum seeds we explored began their long journey toward becoming galaxies, stars, and, ultimately, the complex structures that make life possible. When inflation concluded at around 10^32 seconds after the Big Bang, the observable universe had grown from smaller than a proton to roughly the size of a grapefruit. But this grapefruit-sized cosmos was utterly unlike anything in our experience. It was filled with a hot, dense plasma where temperatures exceeded 10^28 degrees Kelvin, billions of times hotter than the core of the Sun. At these temperatures, no complex structures could exist. Even protons and neutrons were torn apart into their constituent quarks and gluons. This era, known as the quark epoch, lasted until about 10^6 seconds after the Big Bang. During this brief but crucial period, the fundamental forces began to take their modern forms. The strong nuclear force, which binds protons and neutrons together, separated from the electro-weak force. The universe was filled with a seething soup of quarks, antiquarks, gluons, electrons, positrons, neutrinos, and photons, all in thermal equilibrium at temperatures that made the interior of stars seem frigid by comparison. Imagine trying to build a house while the entire construction site is on fire, with temperatures so high that not only would your building materials melt, but the very atoms they're made of would be torn apart. This was the challenge facing the universe in its early moments: how to create stable structures when the available energy was sufficient to destroy any structure that tried to form. The solution came through one of the most fundamental processes in physics: expansion and cooling. As the universe continued to expand, the energy density decreased, and temperatures began to drop. This cooling wasn't like letting a cup of coffee sit on your desk. It was a rapid, relentless decrease driven by the stretching of space itself. As space expanded, the wavelengths of photons were stretched, reducing their energy and thus the temperature of the cosmic plasma. By the time the universe was 1 microsecond old, temperatures had dropped to about 10^12 degrees Kelvin, still incredibly hot, but cool enough for quarks to bind together into protons and neutrons. This transition, called the QCD phase transition for quantum chromodynamics, the theory that describes the strong force, marked the birth of the first composite particles in cosmic history. During this microsecond transition, the universe underwent what physicists call quark confinement. Quarks, which had been free to roam throughout space, suddenly found themselves permanently trapped inside protons and neutrons. It's as if the universe suddenly decided that quarks would never again be allowed to exist alone. They would only be found in groups of 2 or 3, bound together by the strong force. The mathematics of this process reveals something beautiful about the nature of physical law. The strong force that binds quarks has an unusual property. It actually gets stronger as quarks are pulled apart. It's like a cosmic rubber band that becomes harder to stretch the further you pull it. This means that isolated quarks require infinite energy to create, effectively making them impossible to observe in nature except during those first few microseconds of cosmic history. As the universe continued to expand and cool, reaching temperatures around 10^9 degrees Kelvin, at about 1 second after the Big Bang, another crucial threshold was crossed. Free neutrons, which are unstable when isolated, could now bind with protons to form the first atomic nuclei. This process, called Big Bang nucleosynthesis, represents one of the most precisely calculated and observationally confirmed predictions in all of cosmology. The story of nucleosynthesis reads like a cosmic chemistry textbook written in fire. When the universe was between 1 and 20 minutes old, protons and neutrons combined to form deuterium, heavy hydrogen, helium-3, helium-4, and trace amounts of lithium-7. But here's the remarkable thing. The relative abundances of these elements depend entirely on the conditions during those crucial 20 minutes. The density of protons and neutrons, the expansion rate of the universe, and the fundamental constants of physics. The predictions of Big Bang nucleosynthesis are extraordinarily precise. The theory predicts that about 75% of normal matter should be hydrogen, 25% helium-4, with tiny traces of other light elements. When astronomers measure the abundances of these elements in the oldest stars and gas clouds in the universe, they find exactly these proportions. This agreement is so precise that it constitutes one of the strongest pieces of evidence for the Big Bang model. But nucleosynthesis came to an abrupt halt after about 20 minutes. By then, the universe had expanded and cooled enough that nuclear reactions could no longer occur. Temperatures dropped below the threshold needed to overcome the electromagnetic repulsion between positively charged nuclei. The cosmic nuclear furnace shut down, leaving the universe with a specific mixture of light elements that would persist for hundreds of millions of years. This brings us to one of the most mysterious periods in cosmic history, the Dark Ages. Nucleosynthesis ended. The universe entered a long period of relative calm. The cosmic microwave background, the afterglow of the Big Bang, was emitted when the universe was about 380,000 years old and had cooled enough for electrons to combine with nuclei to form the first neutral atoms. This process, called recombination, made the universe transparent for the first time, allowing light to travel freely through space. But there were no stars yet, no galaxies, no sources of light, except the slowly cooling glow of the Big Bang itself. The universe was filled with a cold, dark gas of hydrogen and helium, with tiny density variations left over from inflation slowly growing under the influence of gravity. During this period, which lasted several 100 million years, the universe was literally dark. No light sources existed, except the increasingly red-shifted glow of the cosmic microwave background. The end of the Dark Ages came with one of the most dramatic events in cosmic history, the formation of the first stars. Gravity had been working steadily during the dark period, amplifying the tiny density fluctuations from inflation. Regions that were slightly denser than average attracted more matter, becoming denser still. This process of gravitational collapse continued for hundreds of millions of years, until the first gas clouds became dense and hot enough to ignite nuclear fusion. These first stars were nothing like our Sun. They were massive monsters, perhaps 100 to 1,000 times more massive than our star, burning their nuclear fuel at a ferocious rate. They lived fast and died young, exploding as supernovas after just a few million years. But their brief lives changed the universe forever. For the first time since the Big Bang, nuclear fusion was creating elements heavier than lithium. Carbon, oxygen, silicon, iron, and all the other elements necessary for rocky planets and complex chemistry. The formation of the first stars marked the beginning of what cosmologists call the Rayonization epoch. The intense ultraviolet radiation from these early stars began to ionize the neutral hydrogen gas that filled space, creating bubbles of ionized gas around each star. As more and more stars formed, these bubbles grew and merged until the entire Universe was once again filled with a plasma of ionized gas, but now at much lower temperatures than during the early universe. This process of reionization was recently observed in unprecedented detail by the James Webb Space Telescope. JWST has detected galaxies that existed when the universe was less than 400 million years old, showing us the cosmic dawn when the first stars began to shine. These observations have revealed that early galaxies were surprisingly massive and organized, suggesting that the process of structure formation in the early universe was even more rapid and efficient than previously thought. The role of dark matter in this cosmic construction project cannot be overstated. While ordinary matter was busy forming stars and galaxies, dark matter was quietly building the gravitational scaffolding that made it all possible. Dark matter, which doesn't interact electromagnetically, could begin clumping together much earlier than ordinary matter. By the time the first stars formed, dark matter had already created a vast cosmic web of filaments and nodes, a gravitational framework that guided the formation of the first galaxies. Think of dark matter as the architect of cosmic structure, drawing up the blueprints and laying the foundation, while ordinary matter served as the contractor, filling in the details with stars, gas, and eventually planets. Without this dark matter framework, the universe would be a much more uniform and boring place. The galaxy clusters, cosmic voids, and intricate cosmic web that characterize today's universe all owe their existence to the gravitational influence of dark matter. Modern cosmological simulations can follow this process from the initial quantum fluctuations through to the formation of the first galaxies. The Illustri's simulation and its successors have modeled volumes of space containing millions of galaxies, showing how cosmic structure evolves over billions of years. These simulations reveal that galaxy formation is a messy, chaotic process, with smaller galaxies merging to form larger ones, gas being stripped away by galactic winds, and massive black holes regulating star formation in galaxy centers. But perhaps the most remarkable aspect of this cosmic construction story is how it connects the smallest and largest scales in the universe. The quantum fluctuations that were stretched to cosmic scales during inflation determined where the first stars would form billions of years later. A quantum uncertainty that began smaller than 10 to 35 meters eventually became a galaxy cluster spanning tens of millions of light years. This connection between quantum and cosmic scales reveals something profound about the nature of information in the universe. The pattern of galaxy distribution we observe today contains information about the physics of inflation, the properties of dark matter, and the fundamental constants of nature. In a very real sense, the cosmic web is a fossil record of the universe's quantum infancy, preserved in the arrangement of billions of galaxies across space. Recent observations have begun to decode this cosmic information. Surveys like the Sloan Digital Sky Survey and the Dark Energy Survey have mapped the positions of millions of galaxies, revealing the statistical properties of cosmic structure in exquisite detail. These observations allow cosmologists to test models of inflation, constrain the properties of dark matter and dark energy, and even probe the fundamental nature of gravity itself. The story of cosmic evolution from quantum foam to galactic architecture also highlights the remarkable fine-tuning of physical laws. The formation of stars requires a delicate balance between gravitational collapse and nuclear fusion. The synthesis of heavy elements depends on precise nuclear reaction rates. The formation of galaxies requires dark matter to have exactly the right properties to provide gravitational scaffolding without overwhelming the formation of ordinary structures. If any of these parameters were significantly different, the universe might never have developed the complex structures we see today. Too much dark matter and ordinary matter would be too diffuse to form stars, too little, and gravity wouldn't be strong enough to overcome the expansion of space. The nuclear reaction rates that determine stellar evolution are similarly fine-tuned. Small changes would prevent the formation of elements essential for rocky planets and life. This apparent fine-tuning has led some cosmologists to propose the anthropic principle, the idea that we observe particular values of physical constants because only universes with those values can produce observers capable of measuring them. If inflation creates an eternal multiverse with different physical constants in each pocket universe, then the apparent fine-tuning of our universe might simply reflect selection bias. We exist in one of the rare universes where complex structure can form as we stand here today. 13.8 billion years after the Big Bang, we're living in the mature phase of cosmic evolution. The universe has grown from that grapefruit-sized plasma to a vast expanse containing over 100 billion galaxies, each with hundreds of billions of stars. The expansion continues, driven now by the mysterious dark energy that makes up 68% of the universe's total energy density. Yet, the story is far from over. Star formation continues in spiral galaxies like our own Milky Way. New planets are forming around young stars. The cosmic web continues to evolve as galaxy clusters merge and grow. On the longest timescales, the expansion of space itself will eventually overcome all gravitational binding, leading to the heat death of the universe when the last stars burn out in the distant future. But that cosmic ending is still trillions of years away. For now, we live in what might be considered the golden age of cosmic evolution, a time when stars are still forming, planets are still coalescing, and complex chemistry is creating the conditions for life throughout the universe. The quantum fluctuations that began when the universe was smaller than an atom have blossomed into a cosmic garden of unimaginable beauty and complexity. In our final section, we'll return to that marble you held at the beginning of our journey, armed now with the full knowledge of how something so impossibly small became everything we see, touch, and experience. The universe's story is ultimately our story, a tale of quantum uncertainty becoming cosmic certainty, of simple laws creating infinite complexity, and of how the smallest possible beginning led to the largest possible adventure. Take that marble back into your palm. Feel its weight, its smoothness, its solid reality. Now you know its secret, and the universe's greatest magic trick. This marble, this seemingly simple object, represents something far more extraordinary than we imagined when our journey began. It's not just a metaphor for the early universe. It's a reminder that everything we consider real and substantial once existed in a state so alien, so impossibly compressed, that the marble itself contains more space than the entire observable universe once did. When you hold this marble, you're holding something roughly 10.24 times larger than the universe was during the Planck epoch. Every atom in this simple sphere, the silicon, the oxygen, the trace metals that give it color, was once part of that primordial quantum foam, crushed into a space smaller than the nucleus of the atom you're holding. The photons bouncing off its surface and reaching your eyes have traveled through a space that has expanded by a factor of more than 1 trillion since those first moments. But here's the most profound secret. The marble exists because the universe was small. If the early universe hadn't been compressed to those impossible densities, if quantum fluctuations hadn't been stretched by inflation, if space itself hadn't expanded faster than light, none of this would exist. The marble in your hand is a direct descendant of quantum uncertainty, a solid manifestation of the cosmic expansion that began 13.8 billion years ago. The atoms in this marble were forged in the hearts of stars that formed around gravitational seeds planted during inflation. The calcium came from the explosions of massive stars, the silicon from smaller stellar deaths, the traces of iron from cosmic catastrophes that scattered heavy elements across space. Each element carries within it the memory of cosmic evolution. From quantum foam to stellar furnaces to the quiet chemistry that formed this simple sphere. When you roll this marble across a table, you're witnessing the same physical laws that governed cosmic inflation, stellar nucleosynthesis, and galaxy formation. Gravity, electromagnetism, the strong and weak nuclear forces, all operating at human scales, but following the same mathematical principles that created the cosmos. The marble's trajectory through space-time curves space-time itself, just as massive galaxies do, though by an amount so tiny it's unmeasurable. As you look beyond the marble to the night sky, remember that every point of light represents a stellar system that began as a quantum fluctuation smaller than this sphere. The Milky Way galaxy, with its 400 billion stars, traces its lineage back to a density variation that was once smaller than the marble you're holding. The cosmic web that connects galaxy clusters across billions of light-years emerged from patterns that could have fit inside this simple object. So how big was the universe right after the Big Bang? It was smaller than your marble, smaller than anything you can imagine, yet it contained the seeds of everything you can see. It was a moment when size had no meaning, when space and time were born together, when quantum uncertainty became cosmic destiny. The next time you hold a marble, or see a child playing with one, remember, you're witnessing the universe's greatest achievement. From quantum foam to cosmic architecture, from uncertainty to certainty, from smaller than an atom to larger than imagination. The universe's story is the marble's story, and now it's yours. What does the marble tell you about your place in this cosmic tale?